Section 7.3 is about the law of cosines. In the earlier section on the law of sines, we saw how to apply the law of sines to solve cases 1 and 2, case 1 being side angle angle or angle side angle, and case 2 being the most interesting case mathematically, side side angle. These remaining two cases, cases 3 and 4, are for the situation side angle side and side side side. Here's a good pun that is actually very, very true. The law of cosines complements nicely the law of sines. The law of cosines is used an awful lot in courses like physics, especially when they talk about things like vectors and forces. Here's the law of cosines stated in the textbook. It kind of looks like there are three equations, and I guess there are, but really it can all be thought of as just one single incident. Notice how in a triangle with sides little a, little b, little c, and corresponding angles, how these formulas are kind of symmetrically related. Here's lowercase c, here's uppercase c, lower b, upper b, lower a, upper a. And then in this case, c would be the odd guy out between a, b, and c. And so then this is the other two squared, and it doesn't matter which order, of course. Here, in this case, the odd guy out would be b, and so the other two, being a and c, they're squared and added, and same kind of thing here. So notice here, the odd guy out is b, so the other two, the siblings, are a and c, and so here they're related symmetrically, and here they're related symmetrically also. So the upshot is, if you can remember that pattern in one of these, then it's for free that you can get the other two. Now, just like the law of sines, the law of cosines is valid for any triangle, not necessarily a right triangle. But let me start off with the case here for a right triangle, and then we'll move on from there. So here's a right triangle. Let me label the hypotenuse C. That's the side opposite the right angle. And then the two legs A and B. Now you know to write down the Pythagorean identity, c squared equals a squared plus b squared. One of the most famous equations in all of mathematics for how the hypotenuse of a right triangle is related to the two legs. So in the right triangle case, this angle C, this is little c and this is big C, the angle C is a right triangle, obviously, and so that would be a 90 degree. Now let's look and see what happens when this angle C is no longer a right angle. So in this case, C is what's called an obtuse angle. It's greater than 90 degrees. And over here, C is an acute angle, so it's less than 90 degrees. So this guy here is a transition between these two cases. The idea is that I've tried to draw these two triangles to have the same side lengths A and B as I have up here. So assume that this A is that A, this B is that B, etc., etc. So notice how what's happened in this case is that the side C has gotten longer. That's in the case when angle C is greater than 90 degrees. And in this case, when the angle C is less than 90 degrees, this is get shorter than it was up here. Now I'm going to write down the law of cosines for the case when C is the odd guy out. So I start that off with c squared equals a squared plus b squared, just like I would write down for the Pythagorean triangle identity case. Now, here comes the extra piece. So the extra piece here is minus 2ab. So notice how a and b are partners. C is the odd guy out. And then here comes cosine of angle C. So I've got odd guy out, partners, partners. So this formula that I just wrote down is in fact the law of cosines in that variation shown over on page 572, this one right here. Now let's see why this law of cosines kind of makes sense and why this piece right here is what you would call a correction term to the case of the Pythagorean theorem when you are in the special case of a right triangle. So in this case here of the acute angle, where the angle C is less than 90 degrees, well, in that case, the cosine in the first quadrant, the cosine of an angle less than 90 degrees, is positive. So this guy is positive, so this is positive, so that means that I'm subtracting a positive number. So that means that this c squared, or c or whatever, is going to go be less than a squared plus b squared, right? When you kind of scrunch these two legs together, then this side is going to get shorter. And here's the correction factor for that shortening. Now in the case of the obtuse angle, where the angle C is between 90 and 180, well then the cosine in the second quadrant, the cosine of C is going to be negative. So I have a negative, negative. So this thing here is going to be a positive. So I'm taking a squared plus b squared, I'm going to be adding something. Adding because negative, cosine C is negative. Negative, negative is positive. So that means that this side is going to get longer in the case when this angle over here, is greater than 90 degrees. Right? So if you're up here and you kind of open this angle up by pulling this, swinging this over here, then C is going to get longer. And that's showing right here. This is the correction term, the lengthening. This is negative, so we're adding something to a squared plus b squared. So let's display the law of sines and the law of cosines together here. What I like so much about the law of sines is that it's just so symmetrical. I mean, my gosh, just look at the symmetry there. Once you see this a couple times, there's no way you could unforget it. But now, the law of cosines, well, you know, it's actually probably used a lot more in physics and such than the law of sines, and it has a lot more application. But it's kind of hard to remember and maybe easy to forget. Sure, you can write down the Pythagorean piece here, c squared equals a squared plus b squared. But then you got to kind of remember, well, you got to remember the minus sign, or was it a plus sign? You got to make sure you don't forget the 2. So there's pieces of stuff in this formula that you can lose in memory over a few months. So the law of cosines is more forgettable. The law of sines, I think, is just unforgettable. It's so beautifully symmetric. But back to the very appropriate pun, the law of sines and the law of cosines complement each other in applications. Let's look to see how the law of cosines is used in a side angle side situation. So here we've got little a and little b to be 2 and 3, and angle C is 60 degrees. It's drawn over here, a little bit hard to see. Angle A, and over here is little a, which is 2. And then angle B up here, and here is little b, which is 3. And then C is 60 degrees. So here's the law of cosines written out. I know little a, little b, and big C, so I can substitute into that just numbers, those numbers there, and plug and chug and get C equals the square root of 7. Next, we'll use the law of cosines to figure out angle A. What we know so far is the 3 side lengths, little a, little b, and we've just figured out little c. Of course, we know angle C. So if we can figure out angle A, then by the fact that the 3 angles add up to 180, we know angle B. So we'll use the law of cosines in a different variant to find angle A. So now I just kind of say, okay, this is the odd guy out, little a, because I want to find big A. So here, this is sort of like a Pythagorean theorem, but then I've adjusted it with the law of cosines correction term. Notice A, and then B and C are the pair, and they enter here symmetrically. So I can solve this equation for cosine of A because I know little b, little c, and little a. So here they've solved that equation for cosine of A. And then you take arc cosine of what you got there, and there we go. Finally, let's look at the case of side, side, side. So in this example 2, they've given us the 3 side lengths, 4, 3, and 6. Here's our triangle. Labeled correctly, right, because 6 is side C, so that means that this angle has to be big C. Same stuff for angles A and B. They have to be opposite the sides that are given, little a and little b. So we use the law of cosines to solve for cosine of A in terms of the 3 side lengths. And so do the arithmetic, we get 29 over 36, take arc cosine, and there we go. We do the same type of thing for angle B. We use the different variant of the law of cosines to solve for cosine of B. There it is. And so taking our cosine, we get that. We don't have to go through all that pain again for angle C, because since we know big A and big B, we just use the fact that the 3 add up to 180 to get C.